This is the potential. And if I were to find out the electric field at the point X due to the dipole, I will get Kp some factor 2 over 3 R cube to lowest order. So the electric field has 1 over R cube dependence in electric dipole. So if I were to make a plot, if this were my R and this were my strength of the electric field, if I had a point charge, the dependence is 1 over R square. And for a dipole, the dependence is 1 over R cube. Now, why am I doing this? I'm doing this because of two reasons. The first reason is that if I can generate an electric dipole, far away from that electric dipole, there is going to be a potential. And far away from the electric dipole, there is going to be an electric field. If the heart is a dipole, which I'm going to show how it is a dipole, it's going to produce an electric field far away. And why am I considering an electric field in addition to the potential? Because the electric field is a vector. Remember this, the electric field is a vector. So this must have a vectorial sign on top of it, which means that this electric dipole moment must also be a vector, right? So if this is a vector, there has to be a vector here as well. So the electric dipole moment is a vector. And how do we define the direction of this electric dipole moment? P is a vector, is given by the amount of charge Q, and D becomes a vector. And what is D? If I have a negative charge and a positive charge, then if I draw an arrow from the negative charge to the positive charge, that arrow will be in the direction of the electric dipole moment. So I define my displacement vector from the negative charge to the positive charge. That's how I come up with a consistent definition. And if you look at the example over here, can you tell me what direction is the electric field pointing in at this point X for this particular configuration? Left or right? Right. Why? Because the positive charge is closer to the point X. The positive charge produces a field that points away from the positive charge. So the electric field is pointing to the right, and so is the electric dipole moment, pointing from the negative charge to the positive charge. Got it? Now, how does the heart act like an electric dipole? That's the next question. How on earth is the heart like an electric dipole? That's the question. Next 5 minutes on this question. Any questions from your end? Suppose I draw a myocyte, a single cell, just one cell. Now in the resting state, the inside of this cell is negative in the polarized state. The outside is positive. Right. Now, at each point, there is an electric dipole moment, right? Separation of positive negative charge means electric. So there's a dipole moment here, upward, 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 downward, 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 rightward, rightward, upward, upward, leftward, leftward, leftward. Now, all of these are vectors. roughly the same magnitude. And when you add these vectors, what will be the resultant? When you add vectors pointing in all these directions, what would the resultant look like? 0, right? Your vector pointing to the left, vector on the right, they both resultant is 0. Up, down, resultant is 0. So this cell in its polarized state does not have an electric dipole moment. So polarized, the electric dipole moment is 0. Now let's move to that part of the blackboard. I'm so sorry, I forgot to